A long time ago, before SPICE, if a circuit designer wanted to know how a tube or a transistor would perform as an amplifier without actually building one, he would use the characteristic curves of the device and plot lines through them, which graphically represented the static and dynamic loads for the amplifier. Not surprisingly, those lines are called load lines, and they can be quite useful to visualize the operation of your amplifier. I'm going to use a real example in this tutorial. I will start with the initial version of the 2SK180 light bulb amplifier called LAMP. I hope you enjoy the double entendre. Then I'll conclude by showing my final configuration, if there is such a thing in this hobby. It all starts with the characteristic curves for the gain device. You're probably familiar with these already, and you'll recall they're made by measuring the drain current while sweeping the drain voltage, holding the gate to source voltage constant. The curves for your load line diagram must cover the range of voltage and current where the amplifier will operate. Next, we'll draw a line through every voltage and current point at our selected power dissipation limit. In this diagram, the limit is at 75 watts. When we choose our operating point, we'll keep it on or below this line, or risk damaging our transistor. For the moment, let's assume our power supply voltage is fixed at 50 volts. Our static load, we're using a couple of light bulbs here, have a resistance of around 11 ohms. The maximum voltage we can place across our light bulbs is limited to the supply voltage, so we make a mark at 50 volts. And the maximum current we can pass through the light bulbs is 50 volts divided by 11 ohms, roughly 4.6 amps. So we'll make a mark there and connect the two marks. This dotted line is called the static or DC load line. The quiescent point or Q point lies along this line. We also call this the operating point. Here the Q point is at 28.5 volts and 2 amps. The dynamic load line or AC load line is a line which represents the AC load. In this case, the light bulbs in parallel with our 8-ohm speaker. The dynamic load line passes through the Q point, and its slope is equal to this effective load resistance. We use the dynamic load line to analyze how our gain device will perform when amplifying AC signals. Now back to the operating point. Where we place the operating point depends on our design priorities. If we're primarily concerned with maximum voltage swing, we'll probably place it somewhere near the middle of the load line. This is a general cookbook approach. Draw the load line, place the Q point in the middle, and go for a coffee. There's nothing wrong with this approach, and it will maximize the power we can deliver to the load and give us symmetrical clipping. Alternatively, if our goal is minimal distortion at low power, the Q point might end up somewhere else on the static load line. This is our approach, where we are prepared, if necessary, to trade a little bit of output power or clipping symmetry for really good performance at a watt or less. And we can certainly aim for both by tweaking the operating point and load. Once we've drawn the dynamic load line, we can visually analyze how it will behave when we introduce a signal between the gate and source. The sine wave shown here is around 2 volts peak to peak. At the output, we get a sine that swings from around 24 volts, point A, to 33 volts, point B. That's about 9 volts peak to peak out for 2 volts peak to peak in. Houston, we have amplification. If we increase the input signal, we also increase the output. But eventually we hit some limits. Here our Q point lies below the center of the load line, and we start to clip the sine at point B on the negative going part of the input signal. Here's what it looks like on the oscilloscope. Remember, the amplifier inverts the input. We're clipping at about 9 or 10 volts peak, so our maximum power before clipping is around 5 or 6 watts. Alright, Now we know about the gain and output power of our amplifier, but what about distortion? Ideally, the gain of our device will be uniform throughout the swing of the sine wave. If it isn't, our sine wave gets squished and stretched, adding new sine waves to our output occurring at multiples of the original sine frequency. That's harmonic distortion. We can see the uniformity of gain in the characteristic curves where the load line intersects the traces. We can also create another useful graph called the dynamic characteristic by plotting those intersections with the input voltage on the horizontal axis and the output current on the vertical axis. This line represents the transfer function of the amplifier. A transfer function tells us what we'll get out for a given input. If the gain of our device is perfectly uniform as shown here, the dynamic characteristic will be a perfectly straight line. This is a truly linear transfer function, meaning the output will be an exact scaled replica of the input throughout the range of input. No harmonic distortion. Now back to the real world. You can see the dynamic characteristic is not perfectly straight, it bends in places. Asymmetric curvature will produce even harmonics, while symmetric or S-shaped curvature will produce odd harmonics. Now you're probably starting to see how we can influence the shape of this characteristic by changing where the load line intersects with the device curves. One way to do this is to leave the cue point where it is and alter the load resistance. Or we can move the cue point around. Here's an example of what it looks like on the distortion analyzer when I move the cue point. Here I'm making small adjustments to the bias, which changes the voltage on the drain and the drain current. You can see how both the THD and the gain move around as I do this. That's because I'm changing where the load line and device curves intersect. The slope of the load line remains the same, but it's cutting across a different part of the characteristic curves. Here's what that looks like in the time domain. The top trace is the input and the bottom trace is the distortion. You can see how subtle changes in the cue point change the character of the distortion. And here's what it looks like in the frequency domain. You can see how the magnitude of the harmonics changes with the cue point. In the final version of the amp, I changed the load and the cue point. The operating point is now at 36 volts, 2.1 amps, and the load is around 23 ohms. This required a B+ change to 84 volts. Now we can get 9 or 10 watts before clipping, and the distortion at a watt is nearly half of the original. Okay, well I hope this video has helped you to understand load lines a little bit better. You probably won't actually spend a lot of time drawing load line diagrams. After you've gotten a little bit of practice, you'll probably use this in mostly a conceptual way. Remember, there isn't just one right answer or one sweet spot, and you define what the sweet spot is. I mean, it depends on your listening tastes, and you have to try different things and find out what you like. It's not realistic to think that you're going to eyeball 0.1% THD on a load line diagram, and there are no algorithms to follow or formulas to plug in. You have to build one of these and start tweaking until you find something you like. Simulation isn't likely to deliver the goods either, unless you have an exact model of the actual transistor you're using. That is to say that the results aren't going to agree exactly, and load line cancellation can be a very subtle thing. And when you're talking about distortion in the parts per million, it's unlikely that you're going to get exact results. On the other hand, it certainly can help you understand conceptually what's happening with cancellation. So I'm not saying you shouldn't simulate. Just understand that if you get to 0.001% distortion in your simulation, that probably might not translate to the real world. And finally, speakers aren't really resistors. You know that your speakers have an impedance that changes with frequency, and some of those changes can be pretty big. And each of those impedances is really a different load line. So you can imagine how all of those different load lines sweep out an ellipse. And that's okay. We continue to use the resistive model, and it does a decent job for us. You don't have to make yourself crazy worrying about the elliptical load line. Okay, that's all for this time. Don't forget to ask questions. You can post those in the comments section below, and don't forget to leave your comments. And please don't forget to subscribe if you haven't subscribed yet. That's the best way for me to know if these videos are useful. And don't forget to help each other out. There are very, very few of us interested in this stuff, and it's certainly not a competition, and we're all learning. And so don't forget to help each other in the learning process. And lastly, have fun. Get out there and build some stuff, and try things out, and see what you get. And don't forget to listen to your music at the end of it all. That's all. Thanks a lot.